Greetings of the day, dear students. In this video, we are going to discuss about the transformer on load, and we will discuss its circuit diagram and the important terminology, and also we will discuss its phasor diagram if the load is a resistive load, and also we will draw the phasor diagram for on-load transformer with inductive load, and slowly we will discuss one example on this topic, right? Yeah. Now observe, dear students, before watching this video, please watch the transformer on no load concept. Coming to its terminology, V1 is the primary side applied voltage. V1 indicates the primary side applied voltage, and I1 is the current drawn by the transformer primary side current. E1 induced EMF in the primary side, N1 number of turns on primary side, N2 number of turns on secondary side, and E2 induced EMF on secondary side, and the V2 is the voltage available across the load. With respect to the current drawn by the secondary, I2 is the current drawn by the secondary. Now the load which you have connected, and it is going to have some impedance, and ZL indicates the impedance of the load. ZL indicates the impedance of the load. Now phi is the flux linking both the coils. So if a question is given on this topic, first you please draw this diagram, which is very important. Clear? Now because of this current I2 flowing in the secondary, and it used to set up some flux. Some flux will be set up, secondary flux phi2. And this flux is going to reduce the flux which opposes the flux produced by the primary MMF phi naught. This phi2 is going to oppose the phi naught, this phi2. This phi2 is established because of the current flowing in the secondary winding. Some flux phi2 will be established, and that flux phi2 is going to oppose the primary flux phi naught. Now, depending upon the load, whether the load is resistive load, resistive or inductive and capacitive, the angle between voltage and current will depend. If it is if it is resistive load, the secondary side voltage, right, and V2 and I2 will be in phase if it is R. And if it is inductive load, if this is the secondary voltage and it lags the secondary voltage by some angle phi, and if the load is capacitive, of course rarely we will have the capacitive loads, and your I2 will be leading the voltage V2 by some angle phi. So depending upon the load, this load sometimes it can be the combination of both RL or RC loads like that. But if it is a pure inductor, that angle will be exactly 90 degrees. If it is pure capacitor, this phi will be exactly 90 degrees. But practically pure inductor and pure capacitor are not possible, right? So here now if I2 will be in phase with V2 if the load is resistive in nature. Just now I have drawn here. I2 lags V2 if the load is inductive. I2 leads voltage if load is capacitive. These points are important. Next. So the whatever, even though some flux phi2 is established because of the current flowing in the secondary, and it is opposing the phi naught, but overall the net flux will remain constant. The net flux throughout the core, even though it is fully loaded or there is no load, irrespective of the load condition, its value will be almost constant. Now for example, observe here. So what happens? The core losses iron, because of the winding wound on the material core, and this core losses remains constant. The iron losses, which is going to have two components, hysteresis loss and eddy current loss, right? They are going to remain constant from no load to full load. But copper losses or I square R loss will change depending upon the load condition. I square R loss will change because depending upon the current drawn by the load. For example, if you are connected a load like this, whether it is drawing 1 amp or 2 amps or 3 amps like this, depending upon the current drawn by the load, this I square R loss will change. This will change. But hysteresis and eddy current losses, the core losses will remain constant. The copper losses will change. Copper losses will change depending upon the load. Depending upon the load, the current drawn by the load will change. If I changes, I square R also will change. That is what you have to remember. Next, for example, when the transformer is loaded, some I2 dash flows in the primary winding. Some additional current I2 dash along with I1, this I1 I will show here. I2 dash flows in the primary winding, and because of this additional primary MMF N1, I2 dash will be developed, and it is going to develop its own flux phi 2 dash, which opposes the phi 2. So this phi 2 and phi 2 dash now will get cancel out each other, and this I2 dash will be in anti-phase with I2. I2 dash is going to be in anti-phase with the I2. So how do you understand that? For example, if this is I2 in vector notation, now its I2 dash will be exactly opposite at 180 degrees. Here straight line I have not got. I2 and I2 dash will be exactly at 180 degrees out of phase. Right? Now this phi 2 and phi 2 dash will be equal. It will cancel out. This I2 dash will again generate some flux, its own flux phi 2 dash, and this phi 2 dash will oppose phi 2, and those two will get cancel out. So phi 2 equal to the phi 2 dash, but phi 2 is because of what? Phi 2 flux established due to the current I2. So it is given by N2 I2 will be equal to N1 I2 dash. From this, I2 dash will be how much? N2 by N1 into I2. But already we know that N2 by N1 equal to K. Therefore, our I2 dash is equal to K times I2. Very, very important. I2 dash is equal to K times I2. Now, whatever current this I1 is established in the drawn by the primary winding, it is going to be resolved into two components. One is the I0 and the another one is the I2 dash. And if you observe the no load concept, this I0 is again going to get divided into two components. This I0, one is the magnetizing component and another one is the working component. This one is the magnetizing component and another one is the working component. So this I2 dash, now this is on the primary side, and this is the current drawn, some I2. So induced N1 turns, primary side N1, N2, induced EMF E1, E2, and the voltage here the applied voltage is V1, and the voltage available across the load is V2. So dear students, please observe this I1. What I want to say is this I1 is resolved into two components. One is the I2 dash and another one is the I0. Now this I0 is again resolved into two components, IW and IM, right? So now That is what we have written here. I1, I0 and I2 dash. Again I0, working component and magnetizing component. If you recollect from no load transformer basic, working component is equal to the I0 times how much it will be its value, I0 cos phi naught. Magnetizing component, its value will be I0 sin phi naught, where phi naught indicates what? If you remember the no load concept, if this is the current drawn by the no load transformer I0 and this is the flux phi and this is the voltage V1. Now this is the angle between V1 and I0. This is the phi naught. Clear? So here this V1, but now in this context, now what will be our I1? It is a sum of I0 and I2 dash. So first of all we will have some I0 which is at some angle. Now we are having here I2. I2 dash will be, it's quite opposite. Here this is the length I2 dash. You draw some anti-parallel I2 dash here. I2 dash. Now this I0 plus I2 dash will be, you join these two, I0 and I2 dash. I0 and I2 dash. If you join this, you will get the value I1. You will get the value I1. This is what, if it is a resistive load. If it is the resistive load, observe both E2 or V2 and I2 are in phase. We have drawn on the same line. For example, if this is V2, on the same line we have taken I2 also. Both are in phase. This is the case if it is resistive load. Very, very important, dear students. Don't get confused. This is the resistive load. Because of that I have drawn I2 on here. Observe here. If this is V2, I have drawn I2 at some angle phi 2. Very, very important. I have drawn some I2 at an angle phi 2. This is the case when if the load is a inductive load. Inductive load. Now I2 is lagging V2 by some angle phi 2. Clear? Now to get I2 dash, it's quite opposite. It's quite opposite will be your I2 dash. So just extend this I2 in backside, 180 degrees backside. Now this is your I2 dash. Already I0 you have drawn. I0 is this one. Now we want I1. It is a sum of I0 plus I2 dash. So this is I0 plus this dotted line indicates what? This dotted line indicates I2 dash. Exactly parallel to I2 dash. So I0 and this dotted line indicates I2 dash. I0 plus I2 dash is now your I1. I0 plus I2 dash is your I1. So this is the diagram if the load is inductive, and this is the diagram if the load is resistive. For two cases we have drawn. Capacitor we are not discussing. Rarely we will have the capacitive loads. If it is capacitive load, what happens is this current will come towards this side. For example, if this is V2 and we will get I2 like this. I2 we will get like this. And I2 dash quite anti-parallel. We have to draw like this. This one will be I2 dash. This is angle phi if it is capacitive load. If it is inductive load, this side we have drawn. In third quadrant we are getting. If it is capacitive load, in fourth quadrant you will get the current, fourth quadrant. Right? So in this entire discussion, if the load is connected, I1 is equal to I0 plus I2 dash. The value of I2 dash is equal to the K times I2. K times I2. Phi naught is the angle between V1 and I0. If the load is resistive, V2 and I2 will be in phase. If the load is inductive, I2 lags V2 by angle phi 2. Clear? Good. Next. Now let me discuss a small problem on this topic, dear students. A single phase transformer 50H 440 by 1100 volt takes a no load current of 5 amps at 0.2 power factor lagging if secondary supplies a current of 120 amps at power factor 0.8 lag means lagging. The load is inductive in nature. Estimate current drawn by primary. What he is asking is simply is asking us to calculate I1. I1 equal to how much? I1 equal to how much? And from the basics we know I1 equal to, it's a vector sum. Don't think that this is a common mistake. There is a chance to commit. If I say I0 is some 5 amps and I2 dash is some 30 amps. As sir told, I1 is the sum of I0 and I2 dash. If you write like this, the entire problem goes wrong. I1 equal to I0 plus I2 dash. So if you write 5 plus 30 and if you tell the answer as 35, it is wrong. It is the vector sum. Vectors, do you remember the parallelogram law? Square root of I0 square plus I2 dash square plus 2 times I1 I2 dash into cosine of the angle. Now there will be some angle between this I0 and I2 dash. That angle is important. That angle is to be considered. There is some angle between I0 and I2 dash. Dear students, I repeat again, don't think that I0 is 5, I2 dash is some 30, I1 is sum of those two. It's a vector sum. If you add this 30 plus 5 and tell the answer as 35, it is wrong. We will see in this problem, right? Now, the vector sum, the value you will get something less than 35. One hint I can tell you is, you won't get exactly 35. You will get a value less than 35. In this problem, two angles are there. One angle is the load power factor and other angle is the no load current angle phi naught. Phi naught indirectly he gave you. This 0.2 indicates phi naught. Simple, dear students. In this diagram, we are having two angles of interest. One is the angle between V1 and I0, that is phi naught, and the other angle V2 and I2, that is angle phi 2. So if I want now angle between I1 and I2 dash, in this diagram observe, this angle is phi 2. Obviously it's quite opposite. Here the angle will be, this blue line will be phi 2. Our target is to get the angle between which two? Now the angle between V1 and I0, this angle is phi naught. But I want which angle? Angle between I2 dash and this angle we want. I2 dash and I1. So this is our angle of interest. This is the angle we want. Now what will be that angle? Simply this phi naught minus phi 2. Whatever angle that is there, phi naught minus, in this diagram, phi naught minus phi 2. If you take phi naught angle minus phi 2, we will get the angle between V1, sorry, angle between I2 dash and I2 dash and I1. Very, very important, dear students. I repeat again, angle between V2 and I2 is phi 2. Angle between V1 and I0 is some phi naught. but I want angle between I2 dash and I1. It is simply phi naught minus phi 2, phi naught minus phi 2, right? If we know this point, this problem is easy. Now observe here, single phase transformer, frequency is 50 Hz. This indicates primary voltage V1 and this indicates 110 indicates secondary voltage V2. Primary voltage V1 equal to 440 volt. Secondary voltage V2 equal to 110 volt. No load current drawn is 5 amps. And the no load power factor cos phi naught is given. Cos phi naught is 0.2. So phi naught equal to cos inverse of 0.2, 78.46. Secondary current I2 is given 120 amps. Load power factor, so that is the angle between V2 and I2. The power factor cos phi 2 is given 0.8. So phi 2 will be cos inverse of 0.8, 36.54. Now primary current I1 equal to how much? I1 equal to how much? It is a vector sum of I0 and I2 dash. But what about I2 dash? What about I2 dash? I2 dash is K times I2. But K already we know, V2 by V1 equal to K. So V2 by V1 into I2 equal to 110 by 440 into 120. So I2 dash is 30 amps. I2 dash is 30 amps. Now I0 is 5 amps. So indirectly we came up to here. This I0 is 5 amps and this I2 dash is, now we want to find out this I1. This I1 equal to how much? This I2 dash how much we got? 30. And I0, this I0 current 5 amps. I0 equal to 5 amps. Now I1 will be how much? Just now I told, don't just simply add this 30 and 5. It is a vector sum. I0 square plus I2 dash square plus 2 I0 I2 dash into cos of the angle between those two. Now between those two the angle is cos of plus theta or minus theta, you will get the same answer. Because of that phi 2 minus phi 0 is also okay, or phi 0 minus phi 2 is also okay. So 41.92 degrees. So we will get 5 square plus 30 square plus 2 into 5 into 30 into cos of 41.92, 33.88 amps. 33.88 amps. That is what the value of I1. So now our I1 is 30, how much dear students? 33.88 amps. That is what we have drawn in the form of the diagram also. First we will indicate on x-axis this flux and we will draw some I2 120 at an angle phi 2 36.54. First second step we will draw I2. In the second step we will draw I2. It's quite opposite. In the third, first we will draw flux. Second you will indicate the I2. Third you will draw the I2 dash. It's quite opposite, 180 degrees. I2 dash we will draw. Now we will indicate some I0 at an angle with respect to V1. We will draw some I1. In the fourth step we will draw I0. Now exactly parallel to I2 dash indicated dotted line. In the fifth step we will draw this dotted line. Now join this I0 and this fifth point is what? I2 dash. You just simply join I0 and I2 dash and you will get this I1. At last step you will get, at the last step, sixth step you will get I1. That is what, how step by step, simple dear students. First phi naught 5 we will draw and at some angle we will draw current and I0 we will indicate and it's quite anti-parallel. This is will be our I2 dash and a dotted line we will draw and we will join that and this is our I1 current, and this is the voltage V1, and this is I2, right? That is what we have done in this diagram. So that is how we can draw the phasor diagram. If you observe, the angle is lagging, lagging I2 at some angle phi 2. So dear students, if a question is given on this topic, okay, you please highlight this phasor diagrams. If this point I1, I0 plus I2 dash, first thing is this diagram, it gives some good impression. You indicate the diagram, indicate the variable names, write its names, full forms, I1, V1, E1, I2, E2, V2, N2, ZL. So that is the first part. Now the key point is, if depending upon the load, resistive load or inductive load or capacitive load, the angle will be in phase or lagging or leading. That is one point. Next, this I2 dash is equal to K times I2. You want to highlight this point. I2 dash is equal to the K times I2. Now this I1 is nothing but algebra vector sum of I2 dash and I0. This I0 is again divided into two components. One is the working component and another one is the magnetizing component. Now this working component is I0 cos phi 0. Magnetizing component is I0 sin phi 0. You draw this vector diagram or phasor diagram. If the load is resistive, observe the key point is this E2, this I2 and E2 both are in phase. If it is inductive load, you just draw I2 at an angle phi 2 in third quadrant because it is lagging. If it is capacitive, rarely you will get, you have to draw like this. So this is what all about the transformer on load. Transformer on load. Okay, thank you. Dear students, please share this application with as many students as possible. Share with your friends and also friends in different colleges, those who are having this subject, and also to your seniors who are having this subject as a backlog. And this will be helpful to me also. So please kindly share this application with as many college students as possible. Those who are having this subject. Of course, most of the first year students will have this subject. Most of the universities and colleges are having this basic electrical and electronics engineering subject, and depending upon the branch, for some branches it will be in the first semester, for some branches it will be in the second semester, because it is not possible to run for all the students at a time in the first semester itself. For example, if there are 5 branches, for all the 5 branches, if they are having 2 or 3 sections, total some 10 to 12 sections at a time running this course is difficult. So what they are doing is they will split up into first semester for some branches and for some branches in the second semester. In some colleges they will have this subject in the second year first semester. So whatever might be the case, please share this application with your friends and friends in other colleges and some seniors. If they are having this subject as a backlog, it will be helpful for them, and also it will be helpful for me also. Okay, thank you.